Graphics, the nice graphic is a single box plot, multiple box plot, where it has a single graphic with multiple box plots side by side, one for each category of the explanatory variable. But anything that talks about a appropriate quantitative graphic by the explanatory's categories would be appropriate. So if you tell me that an appropriate plot would be histograms by category, that's great. It actually is more information than what I have here, so that's fine. What I'm looking for is to recognize that you're really interested in what does the distribution look like for that quantitative variable by category. Okay. You should be able to pick out and understand explanatory and response variables. You should recognize the empirical rule and be able to work with it. Remember, the empirical rule tells us that for a bell-shaped distribution, 68% of our data lies within plus or minus 1 standard deviation. 95% lies within plus or minus 2 standard deviations, and 99.7 lies within plus or minus 3 standard deviations. So based on that, I could ask you all kinds of questions about the amount of data that I should find in various ranges for this situation. And you should be able to come up with those kinds of answers. And there's examples of the kinds of questions that you might expect like this that are on the practice midterm as well. Okay. As usual, feel free to stop me and ask questions. Gathering good data. You should be familiar with the fundamental rule, and that is that the data must be representative for the question of interest. Obviously, if the data is not representative, there's not much we can do with it, is there? You should be able to recognize the difference between an observational study and an experiment. What makes something an experiment?
You have to alter one of the variables in an experiment, whereas an observational, you can review them.
Essentially, yes. You don't actually alter the variable, but you alter the situation. It is something where you have manipulated the environment, manipulated the situation. So you have assigned people to a control group versus a treatment group, something like that. You've manipulated the situation. You've controlled the environment. That is an experiment. An observational study, you're simply measuring, taking readings from instruments, whatever the case might be. So there's no manipulation of the environment involved. You should understand the difference between populations and samples. The populations are the targets of our inference. They are, in general, impossible to actually measure. Our sample is a subset of that population. Preferably, if we're obeying this fundamental rule here, it's a representative sample, and it contains information that we can actually calculate and work with. Simple random sample is a special form. That's the ideal random sample. Something nothing like what you guys are doing for your projects. Okay? Most of you said something about doing a random sample, and actually the way that you're doing your data collections are not technically random samples, although you do some form of randomization. It's not what I would call a simple random sample by any means. Again, explanatory and response variable, you should know those. Don't worry about confounding variables. That's still up here, and I got to remember to double check the exam and make sure it doesn't show up in the exam either. We're not messing with that this time around. You should be able to recognize the types of biases in various situations. So it would be reasonable to ask you about a particular situation. You should be able to tell me what type of bias is likely to be present and why that bias is likely to be present there. And it should be one of those three categories. For probability and random variables, this is chapter 7 and 8. We should be able to tell the difference between a relative frequency probability and a personal probability or a subjective probability. A relative frequency probability is one that derives from some form of quantitative analysis. So either measuring the number of occurrences out of a large number of trials, measurements based on a large number of trials. You could be basing it on a mathematical model, something like that. That's a relative frequency type probability. Personal probability is just what it says. It is your own personal opinion of what the likelihood is. So that's not based on any hard evidence, hard data. That's based on just your personal reflection.
Are we going to have to compute any probabilities?
No. We didn't actually talk about calculating probabilities in any situation. It might be reasonable to ask you what the probability of getting a 2 on a 6-sided die is, the kinds of things that you all intuitively know. But other than that, no. Certainly not. If you go through the textbook, it's adding probabilities, looking at the probabilities of unions and intersections and all that. We don't have time to get into that in this class. And frankly, it doesn't really help you very much for what we're going to do later on anyway. You should know that a probability is a value between 0 and 1. We should know that the probabilities for a complete set of possible outcomes for a random circumstance must be equal to 1. So if I'm looking at all possible answers to a particular question, the probability of getting a particular answer would be a relative probability. The sum of all those probabilities must add up to exactly 1. So the sum of all probabilities for all possible outcomes must always add up to 1. Random variables, we didn't talk a lot about them, but they're the fundamental thing we're working with. Anytime we're taking random circumstances and assigning numbers to possible outcomes, that is a random variable. We talked about the number of heads in the sequence of heads and tails that you did during the coin flipping experiment. That number of heads is a random variable. Now we used the numbers 0 through 10, didn't we? It would be just as reasonable if we had some other purpose for what the numbers meant to use the numbers 1 through 11. Whatever assigns a number to an outcome of a random circumstance is a random variable. And essentially everything we're going to work with through the rest of the semester will be some form of random variable. Don't worry about continuous versus discrete random variables. We didn't talk about it, and I'm not particularly worried about that in this class. Sampling and the 5 population parameters. We should understand a little bit about sampling distributions. You should recognize that the sampling distribution for a statistic is a fixed distribution based on the population parameters. What is the center of the sampling distribution going to be? We know that it ought to be normal, right? It ought to be that bell shape. Where should the bell be centered at? Okay, if I'm looking at a mean, the bell shape should be centered at the population mean. If I'm looking at a proportion, the bell shape should be centered at that population proportion. Okay, so it always should be centered at the population value. So the values that we get from our samples should tend to center around the true value from the population. The sampling distribution arises because of random sampling from the population, and we're looking at the distribution then of these parameters. That's essentially what we looked at when we were flipping coins. That's what we looked at in our rectangularity experiments, both the first and second version of it. So as we're all looking at sampling distributions for different situations. This was the decision bonsai that I put on the board for the 5 different cases. We start out with a response variable, and we look at a proportion. Which type of variable is this? Is proportions quantitative or categorical? How about means? Which are means? Means are quantitative. These proportions are proportions within a category. So proportions are dealing with categorical variables. So when I go with proportions to the left, means to the right, this is quantitative to the right, and categorical to the left.